Okay, so I say all of Silke. Here we talk about emergent mesoscale correlations in soft active. Thank you.
Thank you very much, Cesare, and I would like to thank the organizers, Christina in particular, for inviting me to come here. Yeah. I wanted to tell you about something which is partially new, so I really would like to hear feedback from everyone, and in a way go slightly against the grain of a lot of the hydrodynamics here at the conference. Yes. So what I'd like to talk about, and I can summarize it actually in essentially one slide, is saying that active driving itself, because it's fluctuating and active, leads to space and time correlations which are mesoscopic, and that matters in the active materials that we're looking at. So in a nutshell, if I take active Brownian driving, so everybody's classic equation here, rotational diffusion, etc., with a persistence time which is 1 over the rotational diffusion constant, then if I put this together with overdamped elasticity, you can solve this, and I'll show you how to solve this. You will end up with a mesoscopic length scale in there. A mesoscopic length scale, you can think of it as, okay, a perturbation which is active, that perturbation diffuses through my system, and on a time scale tau, it has reached a length scale which is just this, the square root of the stiffness of whatever my material is, the persistence time, and the friction with the substrate. So this is very generic, and I'll show you it shows up in many different systems. And yes, I know it's short-ranged, it's RG irrelevant, but I want to convince you that this stuff still matters. So if you care about RG, I think you can, if you can move on for now, yes? So in a nutshell, so okay, promise here. So I think this matters in at least these 4 different systems. So epithelial cell sheets, chiral active Brownian particles, colloidal active strings, and hopefully, and we think, at the edge of a cell sheet as well. So let me try to convince you of this. So to start with, let's look at cell sheets, and like ever since I saw the first movies of what these cell sheets do, and here is a representative example, actually done by my former student Kaya Kostanjevec in Aberdeen. You see they have spatiotemporal correlations which look swirly, yes, so mesoscopic length and time correlations, which if you stare at an active Brownian fluid, look suspiciously like this, yes, and I always thought this to be the case. So you can see space-time correlations both. And of course, I need to say at this point that this question has been considered by a lot of people, of course, and there is now quite a wide literature of ideas of what's going on in these cell sheets, and I will come back on this. Most of these are based actually not on this very simple fluctuating active Brownian motion, but they talk more about cells pulling on each other, but essentially pneumatic properties of cells and possibly hexatic properties of cells leading to defects, correlations, motion, etc. We also doubled in this more microscopically, and I'll come back to this at the end of this talk. What I wanted to focus on right now is how much of this kind of motion, how much of the complexity of cell sheets can be explained if you just look at absolutely most stupid simple models, saying, okay, my cells crawl on a substrate as vector active forces. I will pretend this is active Brownian motion in a system which is a dense liquid or a solid, and I'll see how far that gets me. And I would like to argue it gets me a lot further than it should. Essentially, I think we should have looked at started there instead of looking quite that deeply into some of the other approaches. So if the idea is quite simple, so you can do a bit of pen and paper theory here by saying, let me pretend my cell sheet is a solid, and I'm driving this persistently with random active forces. They're uncorrelated in space, but they're correlated in time with the persistence time, and as long as my persistence time is small compared to the alpha relaxation time of the sheet, so compared to the rearrangement time in my sheet, a linear response approach is not a stupid idea. So if I do this, I say in linear response, I can write my velocity fluctuations are the active driving with the linearized, here is the dynamical matrix of the system. And in fact, because of them, these being uncorrelated, you can solve this thing. So you have just you have an independent fluctuating noise with a time correlation. You can solve everything. You can show that this thing breaks equipartition formally, and you can compute the energy spectrum. So the energy spectrum here will depend on lambda mu, where lambda mu are the eigenmodes of the dynamical matrix. So what you get is an energy spectrum, which depends explicitly on the mode. And I should say, by the way, when the persistence time here becomes very small compared to friction and normal modes, you recover equipartition with a thermal like active temperature driving, so the thing people have called the active temperature for active Brownian particles for a while. Now, it's a bit easier to see what's going on if you go to continuum. And okay, so I've written it here slightly differently. From people in my practice here, this is more like a solid state idea. So I expand everything in the displacement field out in equilibrium state. I assume there's some sort of short-range forces for a dynamical matrix, and here the active driving. And so essentially, I can go to Fourier space. I have a dynamical matrix here, which is going to have shear and bulk modes in them, and I can compute the active driving correlator exactly. And to nobody's surprise, this is a Lorentzian in frequency space, equivalent to an exponential in time space, the exponential decay with a width which we set by the persistence time. Then I can solve this thing going back to longitudinal and transverse degrees of freedom. And if I compute this thing and spend some time how to remember how to do contour integrals, I will eventually be able to compute my velocity correlation functions. I can also compute all kinds of other things, but velocity correlation functions are the ones you can measure in cell sheets in experiments quite easily. And so what you get is a velocity correlation function, in this case, which has both a shear component and a compression component. And the shear is transverse, the compression is longitudinal, and they're both very simple. So they both have a stiffness in them. So bulk plus shear modulus for compression and just shear modulus for shear. And the persistence time and the friction coefficient with the substrate. And so this is so simple that this becomes at this point measurable. And in particular, one smoking gun here is that persistence time goes like this, sorry, length scale goes like the square root of the persistence time scale. You can also show that the mean square velocity reduces with driving. So there's a log cutoff in here in 2 dimensions, and it depends clearly on that length scale, and you get more and more elastic deformation stored in the sheet. That's a way of understanding why this happens qualitatively. Now, of course, so far, this is just some pen and paper. So first thing we did, we looked at this, and we tested this on active Brownian particles. So what you can see here on the left is results from this. So the dots are simulations. The continuous lines is a normal mode description, which is almost exactly on top, which tells us this is a good approximation. I should say this on the left, this is deep in the glassy phase, where we should expect this stuff to work in linear response. And interesting one, the dashes is the continuum theory, and that works very well where it's supposed to work. And where it's supposed to work is the low Q regime here. This spike here, just wanted to mention this spike here is to do with the microscopic structure of the system. This comes from the structure factor of the material, and this is something you should expect in absolutely every kind of dense material. So this is not an unexpected feature. I should say, if you go to the liquid phase, yeah. Now there is no reason for this to necessarily work, but it actually does work. So qualitatively, you can see it here. This one here. Can you tell the difference? Actually, this one is a solid, this one is a liquid. I've scaled the velocity arrows, but otherwise it is the same thing. So what I want to say here we go through the solid to liquid transitions. The first two are solid. The middle two are liquid but slow. The top ones are liquid but fast. And you can see this works very well into the liquid phase as long as I say as the relaxation time of the sheet is roughly comparable at best. The persistence time. I should say more people have looked at this more carefully, including my current postdoc Jan Edwin Keta, and they find some differences in the scaling eventually with activity, but the general idea actually holds further into the liquid phase. So what we did then is says, okay, we say this might be a model for cell sheets, so let me try to actually map it to look at cell sheets. So one thing which you know, that to do cell sheets you might want to use a better model than just active Brownian particles. So the model we used is a self-propelled Voronoi model. So let me very briefly, and I'll come back to vertex models later on, not the main point of my talk here. So for the self-propelled Voronoi model, the idea is that you use, instead of just soft repulsion, use a vertex model for the interactions, the mechanical interactions between particles. Now, the beauty of this approach here is we don't actually care. This is valid as long as I have some sort of short-ranged interactions between my particles. So this should all stay valid for vertex models. But so for vertex models, as you can see here, so you have the same equation of motion, just with every cell being represented by polygonal tiling. And as you can see, this makes perfectly nice liquids, which look a lot like ABP liquids. So we use the vertex model with the same sort of driving, the same parameters, and check this as well. And you see the same sort of emergent length scale. So here, this is a pretty extreme case, but you see the velocity correlations. You can look at this numerically, so you can see the dots in some simulations. I should say this has a different structure factor, so you can see some more interesting bumps in here. But the continuum model still works where it's supposed to work, at low Q, okay? I wanted to say one more thing here, is that there is this idea that this active driving stores things in the elastic sheet. You can actually formalize it into a scaling function of the mean square velocity as a function of the correlation length, and you get like a master curve of your different models, from pen and paper to soft disk and vertex models. And essentially, the shorter your correlation length, the less is stored, and the closer v square is to v0. At the same time, if you have a very long correlation length, your mean square velocity drops drastically, and more stuff gets stored in there. Now, why am I telling you this? Well, first, it's interesting. Second, it actually helped us try to make sense of actual experimental data. So what we used is these things here. This is human corneal epithelial sheets. So for the experts, these are not the MDCK cells you usually have. These are the cells you actually get on the surface of your eye. And this has medical relevance. But as I said, as cell line, they're quite similar to MDCKs, although not identical. So we looked at this data set. We computed the velocity correlation functions. And what we found was something which is pretty much compatible with this. So we see a length scale in there, which is around 100 microns. We can talk about this later on if you want to have some ideas, multiple ideas, but let's move on for that for a second, yeah? So we have a length scale, which is 5 to 6 cell diameters, which you can also see with the sheet underneath, which is very similar to the sort of length scale you see in MDCKs again and again, 5 or 6 cell, around 100 microns, yes? And that's put us with the right scaling on this point on my phase diagram. So strong activity correlated quite far from the thermal limit. And with this, we two pieces together, and with also measuring the time correlation function in the sheet. You can do this one in pen and paper too. It's unpleasant, but you can. Or you can do it numerically, which is what we did here. But you find always the same sort of time correlations, and they're around 2 hours and a bit, yes? So together with these two, you can invert your correlation length. You can make an estimate what your stiffness should be in units of friction. And then you match the mean square velocity, knowing that a lot of this energy is stored in there. And in fact, after a long story, you can actually match things. You can match things quantitatively. So left is cells as soft particles. Right is a vertex model. So I should say in the left one we also have included cell division and that's a separate talk. We can, yeah, but for realism, yes. So okay, you could say, well, how far have we gotten here? It's actually nice because you end up with not that many parameters, and they have meaning, these parameters. Yeah, okay, you have a length scale, so a cell radius. You have a velocity scale V0, you have a rotational noise, so there's a inverse time scale. And then you get this thing here, so stiffness in units of friction, that's an inverse time scale. So it's not, you scale it out in a way so it actually makes sense. Okay, and then you need to have some other inverse time scale for your word and that. But it's all length scale and time scales now. So it should be, we've managed to reduce the units in here to some appreciable degree. Now you could say, yeah, maybe this is a fluke here. Now I don't think so, because we started looking at this in more systems. So we started looking at this with Jakob Nuttbaum, who said, okay, I can do better than your experiment there. I have actually traction forces. So in particular, he can measure the polarization field, so that the integrated tractions per cell with the substrate. And as you can see them here, they are in fact, and it turned out, they're not perfectly uncorrelated. They're slightly correlated with correlation length of something like half a cell or something like this, or slight correlation between neighbors. Now, this could be due to many different things, but the way we chose to model this is by including subthreshold polar alignment between the traction forces. We included a coupling between the angles of the polarity with a J such that you reproduce this numerically, this correlation, but this is well below the flocking threshold. And I could say there's more ways to do this, but de facto include a bit of a correlation kernel in your driving field. Then with this, we're again able to match simulation experiment quantitatively. And the interesting thing is that we were within a factor of 2 of our human corneal epithelial cells. So it started looking like that makes sense of this, yes? So I should say this idea of sort of a mesoscale color in there, Ukshati and Chachinchia, it is recently for crystals, and it seems to be working quite well there as well. I will come back to cell sheets towards the end of my talk, but I wanted to switch gears a little bit in the meantime. Any burning questions? Okay, if not, I wanted to tell you, so there was an interlude, so what we just did actually tells us more things. First of all, it tells us that we should look out for this length scale in other places. So this is ongoing work, almost done, with Amir Shi and Christian Weppe. So the idea is that if you look at something called chiral active Brownian particles, so there's active Brownian particles, but with driving, which is chiral, so it's a normal one plus a persistent chirality, so these things go like in noisy circles if you let them go, one particle after the other. And the interesting thing is they make patterns too, so I should say immediately, this is not chiral active matter like, for example, the oocytes. There are no coupling between the talks. This is also not an odd active elastic material. This is a different class. This is just independent active chiral driving. If you do this though, you get patterns. So this is kind of just by repulsion. So no torque coupling, if that's what you're asking.
No torque coupling.
Yeah.
Repulsion is soft spheres.
Soft spheres or springs, or doesn't really matter really, yeah. So they make patterns, yeah? So what the kind of patterns they make are quite interesting. So depending on rotation diffusion or omega, so chirality, you get different ones. I should say immediately omega equal to 0, so this line here is the same one I just looked at, and you can get, if your rotation diffusion is large, you get nothing, so dynamic disorder, so this nothing in space and time. If you make it small, you will get mesoscopic range order, so this is the same state I just discussed. You make this chiral, you get additional state, so interesting one, CMRO, chiral mesoscopic range order, so spatially correlated and oscillating in time at the same time. So no wave propagation, I should say, you see nothing here, but then you shouldn't because there's no coupling between position and polarization. Then if you drive this even further, you get something called chiral disorder, which is periodic in time but has no spatial correlations. I should say these sort of states, they've been looked at de facto and not interpreted as such, but you can look at the correlations and they fit this by a group of Lisbeth Janssen, so they're somewhere in this range here, as far as we can tell. I'm telling you this one because you can calculate everything for this system again. So you have a N correlator, polarization correlator, which has an exponential decay superimposed by parallel oscillations. If you do this, you break equipartition again formally, you will get an energy spectrum, which is more complicated, depends on the normal mode, but also rotational persistence and omega, and actually not quite a superposition, slightly more complicated, but you can do it. You can compute velocity correlation functions, which have similar shapes to what I showed you, but with length scales, which now depend also, okay, this is the bulk modulus, the shear modulus, and then longitudinal transfers depend on the rotational diffusion constant and on omega again. And this fits very well with, again, normal modes or with the continuum approach. I should say you can do time correlations in pen and paper as well. I don't want to show you the answer, but because it wouldn't fit on the page, but you can do it, and it fits, again, extremely well to what we're seeing. Here are the different lines, I should say. I'm trying to remember which one is which. One of them is just this correlator, and the other one is the velocity, but they both oscillate in the region where you expect it at low rotational diffusion, and then that goes away if you're driving harder. There's yet another region where some of this works, and this is again a completely different system where we think this is relevant, and that's colloidal strings. So this is a project with Bashir's student Di Chen, together with which I'm supervising with Tani Liverpool, and this one was motivated by a completely different system, which is three-dimensional active colloids of the group of Paddy Royal. So I should say the idea of these is simple. Oh no, actually no, it's not simple. I'm taking that back. So we have a charge electrophoresis on Janus colloids, and because of this, these things self-propel. We know this, yes, but at the same time there's an external electric field which induces dipole-dipole interactions, and so the whole thing in 3 dimensions is going to make strings on top of each other. So you have dipole-dipole on top, and then you're translating orthogonal to this in your system. And let me see if this movie will play. You don't see them particularly well, but if you go to small enough packing fractions at large enough electric field, you will see a phase of traveling strings. So as you can see already up here, these are not exactly obvious to image, yes? So the data we have on there is limited, but we wanted to understand, to see if you can understand how that string phase forms. So we went on to simulations, and you can already see that it worked. So the idea here is that we make strings out of with a potential, which is a WCA, so we obtain hard repulsion, with dipole-dipole interactions in such a way that the polarizations are always in the Z direction, which is the direction of electric field. So we assume it's so strong that it always stays coupled. And then if that is because of the Janus architecture, that means the self-propulsion is always in the plane, where the polarization is up-down. So they make strings which are propelled orthogonal to the direction. And okay, you can check out where your string phase transition is, which means you need to go to strong enough polarization strength. But what you see mainly, and you can see it here, is actually a very nice phase of moving strings, but they move in an interesting way. So they're self-propelled, and as you can see also they're fluctuating around the contour with an actually pretty non-trivial length scale in here. So we looked at this thing. So first we characterized it, and so we changed, in fact, not packing fraction or polarization, we changed rotational diffusion constant in ratio of translational to rotational noise. So we looked at this in the plane of active driving, if you want. And so you can see interesting things. So what you can see is actually different behavior. So what you can see is that, okay, and let me see, here is the lifetime of them, that's the mean size. As a function of rotational diffusion, you get strings which are, let me see, lifetime, yeah? So, sorry, one of the first times I talk about this. So if you look at these two movies, so the first one here is in the region of low rotational diffusion, yes? The one on the next movie is high rotational diffusion. So you can see the left one is the first one is very different from the second one. So the first one is here. These are strings which are colliding with each other, which have a short lifetime, and they also have a size which is not always the size of the box. The other one, so the one you see here, is very nearly thermal. These are strings which don't collide, they live essentially forever as long as we can measure, and they also span the box. So the idea is here, these ones, they're not fluctuating along the strings, they're barely moving, and so there's clearly a difference. So we started looking at this, trying to understand this, using a modified version of a Rouse model. And we can do Rouse modes because our particles map essentially to a polymer with no stiffness. So you can quite laboriously work with your WCA and your polar-polar interactions and derive effective stiffness constants, which are different along the plane and along the z direction for this potential. So you can actually do it pen and paper. It's annoying, but it can be done. And then write it as an effective Rouse model with active driving in XY only. And you can compute this thing, and what you will find out for exactly the same reasons as with the active Brownian driving we showed you earlier. This is a time-correlated noise again. You can compute everything. You will end up with this is a solid, you end with overdamped solid, you will end up with the same mesoscopic correlation length, and this time it shows up in the tangent-tangent correlation function. And in the tangent-tangent correlation function, you will find, well, that's a prefactor which depends on an active effective diffusion constant, but most importantly, it has an exponential decay in n minus n prime, which is the number along the polymer, with a mesoscopic correlation length, which again is our old friend, square root of the stiffness of the polymer, the rotational diffusion constant here, and the friction of the system. So it's the same one. I should say this works very well. So you can see the theory here. Then you have different rotational diffusion constants. And you can see the length scale, which is 10 here, then decaying quickly if it becomes larger. I should say you can also see this for much larger, much smaller DR. I can show you if you're interested. One more thing you can do as well, because you remember we have much more collisions when the rotational diffusion constant is lower. What you can do is you can compute the mean square displacement from the zeroth root mode here, and you will find, actually to nobody's surprise really, a persistent random walk with an effective diffusion constant and an effective active velocity, which scales with n. So the effective diffusion constant goes like 1 over n, and the effective velocity goes like 1 over square root of n. And this fits extremely well to our simulation results. And I wanted to say, and since this was inspired by experiments after all, right? Now I wish I could tell you, now we measured this in an experiment, it also fits very well, but it's a very difficult experiment. It's very nearly impossible to entirely get data out. So the only thing we could do, if we had static images, and it's really funny where you convocally scan from bottom to top over time scale, which turns out to be of the same order as V0. And so what you're seeing is, you scan this thing, and what you see there is tilted strings. These strings are tilted not because they are tilted, they're tilted because I'm imaging them as they're actually translating. So from that tilt, with a couple of approximations, of course, you can infer what the actual speed of that string is. And if you do this, you can see that, well, within some pretty generous error bars at least, that the velocity goes down with the string length, with a scaling which is compatible with the square root of n. Now, it is limited, I completely admit this, but maybe it means maybe we can make nicer systems so we can measure this more carefully. How much time do you have? Yeah, okay, yeah. Yes. Let me come back to cells then, and I'll see how far I get. So, cells, cell sheets. Here is a quite storied problem, yeah. So these are MDCK cells, sheets, and this is data from the group of Inke Netke, University of Dundee. And what you can see, you see here in blue are actually my cells, and then in red is the edge, which we've analyzed, and in black is a PRV field. So you can see this cell sheet invading free space, and this is usually when people look at wound healing and try to make sense of how it could close a wound. Now I should say, biologists of course care about this and say there should be leader cells at the front which are pulling this sort of thing. There is, I should say, I'll cite a couple of them later, there is a lot of ink has been spilled in our community trying to explain these things with many different mechanisms. Now, of course, I want to give my own spin on this in a way, and I said, let's look at this carefully again and see how much of what we're seeing here is compatible with this extremely simple, just active driving picture. So, and it turns out, and this is work of my group, here's Sander Kamerad, who is now first year, sorry, this movie has decided to be unhappy again. But you can analyze this quite carefully. And you find something which actually surprised us, because we were looking for an instability here, yeah, and we didn't find one. So we worked at this quite carefully with a lot of data. We managed to look at the spectrum of the cell sheet edge. So we're looking at right here, where does this go? Yeah. So we look at, so here's your edge. You can map it to height, and we're looking at the y coordinate here only for now. And you do your Fourier spectrum, and you find this. Now I look at this and I say, well, first of all, two interesting things. As a function of time, and you can see we're slowing down in time here compared to the beginning, this appears to be reaching something like a steady state. So that was the first thing, which was interesting. The second thing is, I'm not seeing a peak here anywhere. So I'm not seeing evidence of injection of energy at any particular length scale, or the emergence of a particular length scale in here, like I would expect for an instability. Now, we could say it's quite hard, it's quite noisy to get a spectrum. Something easier to look at is a tangent-tangent correlation function, which is much smoother, but you get essentially the same picture here. You get, okay, well, you get a length scale sort of 100 to 200 microns, and the thing appears to be reaching steady state yet again. I should say, by the way, this doesn't reach zero because it's mostly still a straight line in one direction, so there's a residual. In fact, if I look at this, it suspiciously looks like the sort of thing we saw in the correlated strings just before. So the question was, and I should say that length scale 100 looks also again a bit like the length scale we keep seeing in these cell sheets. So we said, well, of course, there's this interesting idea forming here. So let's look what's happening inside my cell sheet. So I should say the spatial velocity correlation functions look like a pretty nice exponential, and they're also pretty much not time dependent. Same sort of correlation length, around 100 microns, as we tend to see in the sheets again and again. We looked at the time velocity correlation functions. Now, if you're looking inside the fingering region, so at the front, that's again an exponentially decaying correlation function with a time scale of like an hour or two. Again, same sort of number as we had for the sheets before. I should say, we do know there is more going on, and if you watch that movie carefully, you will see evidence of like little wave propagation in pieces of it. That leads to things in the time correlation function. We're looking at this, but we think that this is happening probably on top of whatever the basic fluctuating picture is. So we haven't looked at that in detail. So let's start with these ideas. So the idea would be here. Of course, there are a lot of finger formation models. So if I missed your favorite one, I apologize, yes. But okay, it's chemical signaling, curvature and enhanced motility, leader cells with special properties, velocity gradients here by Ricard Allaire, plus a lot of other coupling terms. We talked about them yesterday. There might be a pressure-dependent growth rate, and there's some other ones. But the question is here, so how far do we get if you say, well, correlated inside, some other version of an actin cable, does this happen? And so we set out to look at this. And so what we use is actually something developed by Rasko Sknepnek, his master student Dan Barton, and myself some years ago already for the vertex model, which says I'm taking a standard vertex model, but I'm coupling it to something. So I'm gluing onto my vertex model, and I don't want to get into the lateral angulations and that sort of stuff too much. But I'm taking this, I'm gluing onto the edge something like an active polymer. So it's a polymer with with the stretching stiffness, with the bending stiffness, and with the stretching L0, which is 0, which means that these points want to be next to each other, but they can't because they're glued to the rest of the tiling of the self-propelled Voronoi model, which makes this a contractile polymer at the edge of my cell sheet. Okay, and so if you do this, you get something like this. So what you're seeing here, the arrows, is the velocities. The black here is the edge. And so this thing actually naturally does form correlations in fingers. So that looks, I mean, qualitatively at least rather similar to what you see in the cell sheets edge, with one difference is that this thing is not invading space. And it can't because density is conserved in this thing, so you would need to either include division or some sort of coupling to the height of the sheet. So we started looking at this more carefully, sorry here. So this, by shape index, this thing is in the fluid phase as expected. And I should say you need to be in the fluid phase to reach, and this is a very simple measure, the time to reach 5% in change in length is only finite in that region where it's nice and fluid. Now, we were very confident about this until a couple of months ago, until we started looking at doing this very carefully, and so you can do this. So you get a lot of things which look quite similar. You get the tangent correlation function with the length scale. You get the, of course, you get the spatial and temporal correlations, which look very similar to the ones you see in the cell sheet. Our Fourier spectrum is a bit of a mess, but it appears to have, in this one here, actually, so this is why it's preliminary, and I'll tell you something better in one moment, yeah, is we think the way our edge is glued, this sort of thing, which can make X-ray particles, actually introduce an instability there, but maybe not the one we want. So not quite it, but we can do something else, and we're fixing this one. I hope to show you something nicer soon. But what we can do instead, or in addition, is we can actually map this using more pen and paper results. So this here is an active polymer, which is exactly like the active polymer which I showed you for the vertex model, so stretching and bending, but I'm deriving this with correlated active noise equivalent to the one which I should expect inside my cell sheet, which I've generated using an elastic chain, which I'm also simulating with the stiffness mu. And that looks, again, that makes fingers which come and go in a similar way. And so in ongoing work, we're also mapping this to an interface problem. So you can say, okay, well, no overhangs, etc. Let me map to a height field. And this looks then, and I should say this looks exactly like something like you would write down for a worm-like chain model, if you include bending. So you get overdamped dynamics of the height field, get line tension. So this is actually the tension term goes in here, so Laplacian. And you get a fourth order term from the bending stiffness, and then you derive this with that correlated space-time velocity field at the edge. Now this one you can do in pen and paper, and there's a lot, and Sander has sent me sort of 50 pages of this. I wanted to just highlight one of them, which is a t going to infinity height correlation function. So this has a lot of different things in it, and you can see it plotted here in red, the last one. So it goes flat at low Q, and then it has either exponent 2 or 4, depending where you look. And it is compatible with the spectra we see. Of course, this is the polymer here, and also from the ones from experiment. And I should say, this also makes the tangent correlation functions. So I wanted to say this is work in progress. We're now trying to put all of these pieces together and see how cleanly we are with all of this, but I think it's still promising. If I have a minute or two, I wanted to say there's also something else we're working on. So, as I said, I promised you, I wanted to get back to cell-cell stresses. So we have looked at just the simplest types of active driving now, but we know this isn't quite right. We know these things are pulling on each other, leading to this kind of phenomenology. So something we're also working on is to make better models to include some of these things. And I wanted to very briefly tell you the sort of extra terms you want to include. Now, I'm going a bit technical here, but this is the equations of motion for a vertex model. So vertex model, if you don't know, says every cell is a polygon with an A minus A0 square area term with a P minus P0 square parameter term. That gives you equations of motion for a vertex, which have forces which come from along the junctions, forces which come down on the area. And I just said, to make these systems better, and I think Jan Rosman will talk about this tomorrow, we should not include only dissipation with the substrate, but we should make proper models which include pair dissipation as well, yeah? Then you can put your activity, if you want to look at active stresses, there should be either active tensions, which are along here, this is the tension along a junction here, pieces from a vertex model, plus any active terms, or you could, you could put them into area forces, so that's forces which go inwards along my cell contractile. So there are some from the area term, but you could add active area forces too. So you can do lots of these things. And the sort of things you could model with this is things, for example, like chick embryos, where we see weird active convergence extension shear flows, where in particular you see flows which are such, this convergence extension here in something called primitive streak formation, where things are polarized left-right, but they flow up-down. So I don't have the time to explain exactly what's going on. Just wanted to say that quite laboriously, you can definitely do models of these. They're complex, they're difficult, but if you want to do this seriously, I think one needs to make that step. And I wanted to finish by saying, this was a couple of years ago with Rasko and Kees. I'm now working with my postdoc Jan to do these things more carefully from a StatMech point of view. So here's a very simple model where we throw away where we don't really look at pair dissipation, and we only put fluctuating Ornstein-Uhlenbeck active forces onto these junctions. So this has also again only a persistence time in it and no correlations. So it's the tension analog of the thing which I was showing you earlier. And that it makes some interesting patterns, but something interesting we observed is that this thing does the opposite of a mesoscopic length scale. And you can do this in pen and paper if you want to. So you can do a full model with pair dissipation and here this, where is it? There we go. Yeah, pair dissipation, bulk and shear, substrate dissipation, elasticity, fluctuating active stresses. You can again calculate everything. You get a bit of a mess, but you can get multiple length scales out of this. And I know this looks a little abstract, so let me plot it for you. So what you expect is something actually. You find something where, first of all, you're going to cut off things at high K. So this is a one-dimensional model. Normal terminal would just be flat, yeah? You cut off at high K hydrodynamic length scale. Everybody's telling me, yes, of course, Silke, you just rediscovered what we've known for 30 years, yes? But the one which is more interesting is that the active correlated fluctuations cut off the low Q. So they suppress the low Q fluctuations systematically. So instead of long-range fluctuations, you get the opposite. You get an enhancement of short-range fluctuations. And when you know it, if you put both of these together, this looks almost as if you're selecting a length scale. Just because of these two, you suppress both ends for very simple reasons. And so what you're left with is in the middle. Now, of course, this is a 1D calculation. You should actually look at this in some sort of simulation. So here, this is not done, this preliminary, and without pair dissipation, but we definitely see this is vertex models, low Q cutoff. So this scales like K square as it should for the vertex model. And preliminary high Q will get cut off, but we're not entirely done yet. But I am done yet here, so thank you very much. I think this sort of stuff matters.
Are there questions? Yes.
Could I look at the last set of equations of motion?
Yeah, sorry, that was...
Yeah.
Sorry,
okay,
too
so
fast,
you have a sort of overall damping, that's
yeah.
eta, and then you have these two viscosity-like terms, and you have elasticity.
We have elasticity,
and
so
your stress and your forcing
By forcing in this one.
Your random forcing is completely momentum conserving, is that right?
Yes, so that was the idea. So we
Nice.
said, let's, because we're motivated, I was clearly squeezed too much into this talk, as usual, that for these cell sheets, active forcing is action-reaction preserving because there's really no place for it to go, to crawl on. So that motivates this. So it should be divergence and active stress. So you could make these with these junction forces, which I showed you, are of that class. But in continuum, this will make you momentum conserving, active forces, no way around that. And so
but you might think there should also be a noise at zero wave number because you've got a damping at zero wave number. So why do you choose to leave that out?
I'm not. The damping at zero wave, so I would assume this to show up from here.
Yeah.
That stays in there.
And the sort of random binding, unbinding to the substrate or whatever it is should give you a...
So this was made for places, okay, so the idea here would be that for a cell sheet, that first dissipation is more with the surrounding fluid. So it being surrounding fluid, it can't pull on it because there's nothing to pull on. By the way, with you, if I make a full model, I should have both types of activity. I should have crawling, and I should have pulling, and then, as you can see, it gets messy already. Essentially, you put these together, you can get almost anything, more or less.
But the vanishing of the structure factor at zero wave number is because your noise vanishes and other things don't. Ultimately.
Yes, yes, you can put it that way, exactly, yes, yeah. So exactly, yeah, okay, so.
All right.
Yeah. Okay, you put it right. If you have real thermal fluctuations on top of it, yeah.
I mean, thermal or otherwise, you could even imagine binding, unbinding to a substrate or something.
But if you don't have one, though.
So then why do you have eta u dot? What's the...
Fluid. Fluid you can dissipate, but you can't pull on. At least not if you're a cell. Not this way, yeah.
In this mapping to a semi-flexible polymer, you look at the linear dynamics.
Yes, and we probably, I mean, we're not experts in that, so if there's some,
Because if you really assume that the mapping is such that this is a non-stretchable,
so we assume it's stretchable here.
It's stretchable.
It's stretchable, and what I call lambda here is de facto the tension in the thing. So we spent some time making sure you understood that one properly. So this is the tension, which comes in the first term, yes. So it's a stretchable polymer.
Okay.
Yeah.
Because else there would also be stored length fluctuation that you have to consider. And then the stress propagation changes.
I'd love to chat. I am not sure I'm an expert on this, so I'm trying to understand exactly if you're, So this is what you see here is a simulation of a polymer, one polymer with that driving couple to it, and we managed to get it to fit, so we were happy, but I want to make certain we don't miss anything,
Another question.
Yeah.
Anani?
Just looking at the high correlations here.
Yeah.
So at low Q, the low Q behavior of this high correlation effectively gets a effective temperature scale from the correlation time, but the difference comes in from a correlation length. Is it? Mu gives you a correlation length.
Yes, it does, yeah.
Okay, so the lowest order, only the correlation length gives you a lowest order contribution, and the
Yes, but the correlation length comes because of the time which was in there. Ultimately, it's all the active driving inside, which is responsible. Yeah.
One of the, I guess, on the analysis for the interface, the vertex model, the tangent-tangent correlator at later times seems to have a dip.
Yeah, I don't know why.
Oh, this one, yes.
Yeah, I should say there is. So we were looking at that. I think that the vertex model edge is maybe not quite exactly what we want because it seems to have a secondary instability, which is often. So we thought actually this was what we're looking for, but now it doesn't look like. There's essentially viscoelastic. It can make new nodes if I push against it. So there's a feedback in there. So originally we thought we'd actually see this, but it looks like this is not in fact what's happening in the experiment. So that's likely showing up here, yeah?
This has nothing to do with the weird surface tension of the vertex model that is already present.
What specific? So we have an explicit polymerity edge here. So I think whatever that is, that's going to kill everything. And I mean, making edges in vertex models is very difficult, right? So I should say, this is not like the MIPS edges. There's nothing crossing that boundary. There's an actual real junction there. So it's a bit more pedestrian that way. But yeah, no, I welcome feedback on this because
Okay, I think it's time for coffee now. Thank you very much.